So, gentlemen, we are ready to start our wide bandgap session on GaN, and we had the pre-recorded presentations to the auditorium, and we are now waiting for their requests, and I'm looking. The first request is ready to come. It's a question to all of you. Is it advantageous or not to have a product that is half bridge with two power transistors connected in the same package?
May I take a crack at that?
Yeah, Alex, go ahead.
Okay, the answer is, if it's packaged properly, the answer is yes. At high frequencies, the parasitic power loop inductance plays a significant role in the efficiency of the system. And if I may, I'm just going to share a quick slide here to show you the exact difference between putting two power FETs on the same chip versus having them discrete. And this is, here, share screen. Hang on. Oh, I don't think I can share the screen unless you let me, Bodo.
My backstage is working on it.
All right.
It's Franziska and Holger.
Yeah, for some reason, allow me to share. But...
All right. Well, it allows me now.
Yeah,
okay,
we can see now. Yeah.
Here we go.
All right. So you can see it pretty much exactly. This is just showing the various generations of GaN devices. And the blue and the green is a direct comparison of monolithic versus two discrete devices with the same electrical specs, also in GaN. So that's really the difference that comes from the power loop inductance, and that's quite significant.
Yeah, and if I may also comment on it, if you can see my background here, that's actually a monolithic half bridge. So I agree with Alex. This is the way to go.
I completely also agree what Alex said. What I want to add to this topic is, if it comes then to the integration of the driver, because this is maybe the next question, it must be differentiated. This depends then on the power level, because VisIC is, for example, focusing on high power applications, as maybe shown in the presentation before. So going up to 50, 80, 100 kilowatts, and there the integration of the driver seems to be very difficult and not the right way to do. This is only the extension to the question you just asked.
Yeah.
Yeah, just to add to, I agree to all our previous presenters, and also there are, I think so, the question also relates to multiple die in the same package, where the co-packaged, and that also improves the loop inductance quite significantly. And multiple dies sometimes helps thermally, because if you've got two separate thermal pads, and that can also distribute the heat between two die, which also allows sometimes the higher current carrying capability.
Seems to be a common understanding.
Yeah. Yeah. So there is no, how to say, one solutions fit all, right? And I think how to say Bernd makes actually a right point there, right? How to say, for high power, where thermal actually become more a challenge rather than how to say the integrations of that. So you might actually just consider to integrate a fractions of the driver circuit into the device when we going with, how to say, with high power. But for low power, yes, that is actually very convenient to have, how to say, a full driver integrate to the device.
Yeah, at EPC, we have full integrated power stages up to about 35 amps. And then we have a two-chip solution where we actually integrate the drivers for both the high and the low side, plus the level shift, plus the logic into one device. And then all you need is a low side device to complete the circuit up to 100 amperes. So it's really, you know, exactly the same thing that Cam is saying. At higher currents, you want to probably split the chips up.
Yep.
There is an issue of very high currents and how to parallel these things well. At this point, paralleling would take two forms, either paralleling the complete power loops, or you want to parallel devices, discrete devices. If you parallel discrete devices, which is pretty easy in GaN, you don't want to have onboard drivers and level shifters unless you can synchronize them very well.
Alex, what VisIC achieved in the last months was a sine wave on a motor inverter with an RMS current of, if I'm right, 480 amps. So
that's fantastic.
This is clear that we made a lot of parallelization and had to spread the heat accordingly. Yeah.
Yes, exactly. Yes. So
the upper edge of what is currently, I believe, available.
Yeah, this is optimizing against the actual system requirements because sometimes the integration works for the lower power because the temperature is not that critical where you can go up to 125, but when you are talking about really high power, you would be considering up to 175 degree, which is not possible if you have got driver integrated.
I have to dispute that. I think it's absolutely not only possible, it's very straightforward in GaN. There is that sense that high temperatures somehow pollute the driver circuits and the level shifters, and we've seen no evidence of that well past 175 degrees on our devices. So I think it's true for silicon, though, but just not for GaN.
So your integrated driver is spec'd for 175 degree.
It's not spec'd for that. It's spec'd for 150, but we've certainly taken up to much higher temperatures to verify that it's okay.
Yeah, that's probably where beyond the spec, if it works, that might be, you might consider speccing to 175, then it would be nice.
Yeah, you're absolutely right. Automotive people love it at higher temperatures.
Exactly.
I tell you a joke. There is once an audio system designed in the 90s, which had the control system right above the muffler at Daimler-Benz. So the spec, it was during my time at GE Solid State or Harris. So the spec was a 200 degrees Celsius spec for an IC to perform because the automotive designer put it directly above the muffler in the inside of the body. So things happen and it worked, but it had become extra expensive ICs to make it happen.
Yeah. So you'll have to consider the economic aspect as well.
Yeah.
Whether it's commercially viable. Yeah.
But the advantage of GaN is GaN works really well at high temperatures. You know, the intrinsic failure mechanisms have negative temperature coefficients, so it's kind of just getting going when it's up at 150 C.
Yeah, obviously there are other factors comes in like higher temperature dependent RDS on, so the conduction losses will be quite high as the temperature really goes up. So yeah, we'll have to consider from the system level, and one solution doesn't fit all.
Yep.
Absolutely true.
Yeah.
Gentlemen, we got the next question. It's also to all of you, for hard switching, good performance, the ratio of CGS and CGD should be as high as possible. Does some GaN designers add MIM capacitors to increase CGS, or using the metal 1 and M2 in a smart way to increase this capacitance?
So I'm not sure I agree that for hard switching good performance, the ratio should be as high as possible. I think that the issue, this is a Miller ratio. The issue is actually that the CGD over the CGS1, which is the gate to source capacitance to get it up to threshold voltage, needs to be less than 1. That's the Miller ratio. If it's less than 1, you will never false trigger the device. If you just look for an infinitely higher input capacitance, you'll get a lot of switching losses at high frequencies. So the best thing is to design your device for this Miller ratio to be below 1 under all conditions, which is what we do at EPC. And that's CGD over CGS1.
Yeah, I will agree.
Again,
yeah.
Again, same opinion, and adding some capacitors on the gate to influence that would be, for me, not the right way to do.
Yeah. So same has a wavelength with the Alex here. It's you have to, or at least I say from device has a manufacturer point of view, right? We have to solve that problem, and we can actually solve that problem on the device level, right? I say by reducing actually I say the Miller capacitance and have that has a ratio that is actually performing well over the spec of the device. Not necessary just to pollute the good figure of merits of GaN by adding additional gate source capacitance. It will help, but it's not needed, and it will make your switching losses and your figure of merits much worse than that. So, but it's tempting. It's tempting, but doesn't have to be like that.
Yeah, not only that it will increase the switching losses, it will also increase your driver losses, because now driver need to drive harder.
The switching losses, yeah.
Exactly, yeah. And one of the things you'll have to careful is about the CGD DVDT is the one that is inducing, that current is inducing the voltage across the gate. So as long as that is below your threshold voltage, you are safe. Sometimes obviously negative voltage helps.
And I say it also,
negative voltage is a bad idea. Don't do negative voltage. I'm sorry, Dilder.
Yeah, only for the E-mode devices.
No, don't do it. Don't do it. Don't pollute the world with that advice. That is bad advice. I'm sorry. If you design it with a Miller ratio less than 1, you don't need negative gate drive, and adding negative gate drive adds losses.
Yeah, absolutely. Yeah, for the
well, I disagree.
Bad idea.
I disagree here, Alex. I disagree here, Alex. From a user point of view, this really depends on 2 factors. First of all, you have to look at the devices available. They are what they are, so we have to deal with them. And second, you have to look at the voltage that you operate them at. So if you're operating, let's say, 100 volts, maybe at 200 volts up to, you could do it without a negative voltage. But if you're operating at 400 volts and beyond, and 650, then the negative voltage is needed. But I agree with you. You will increase the losses if you don't do it in a smart way. So you need to do it in a smart way, because everyone knows, or maybe not everyone knows, but we know that if you use it in a dead time during the 3rd quadrant operation with a negative voltage, your forward drop will simply increase. So of course you need to do it in a smart way. But I do see it's necessary in high performance applications where you want to use both high voltages, meaning above 200 volts, and certainly above 400 volts, and in combination with very high DVDT. If you want to switch at the limits and really use the advantage of GaN, then you need a smart way to do negative voltage.
Yeah, we don't recommend for our high voltage devices like 650 volt. We use a very high threshold voltage on our GaN devices. So they come with a +4 volts to avoid any unwanted turnout, especially when you have got a very noisy environment with a very high DVDT and a 400 volt platform or 650 volt that you take your device up to. Then it's a lot of time that you are basically charging your gate with CGD DVDT, and that obviously to compensate for anything. So we recommend 0 to 10 volt, 0 to 12 volt drive without any negative voltage required for the gate. So because threshold voltage is already 4 volts, so that helps unwanted turn-on. Yeah.
And
it
unwanted
comes to the implementation of how you do your GaN device. We are here in this group, companies with different flavors of GaN coming from direct drive or cascode or a P-gate GaN, whatever. So it depends really on the realization of what you do, and that's, I think, the first point you have to look at and then judge.
Well, I would just like to say that if the Miller ratio is below 1 in enhancement mode, P-gate device, a simple device, doesn't need negative drive to turn it off at high voltage or low voltage. But if that's not available, you're going to have to do negative drive. But it's a disadvantage.
Absolutely. Disadvantages for sure. That's why the third quadrant losses goes up quite significantly when you have got the negative drive. And that's not a very good thing for where the designer
as mentioned, you have to do it in a smart way.
Exactly.
So you have to do it only during the time that you need it.
Yeah. And if it's parasitic turn on is actually a concern, right? Let's not forget actually the internal gate resistance as well. I mean, when we look actually at the device, this capacitance ratio, right? It's a lump sum of interconnect capacitance on the cell level, right? But the internal gate resistance is also responsible for that. So we should actually also look into how the device is designed, but not necessarily just like a Miller ratio. But internal gate resistance also have actually an impact on how well it's actually also performed. But I think it can be done and not necessary by induce or including another capacitance to the gate source, which the audience
look at,
asking.
As a device guy, I'm a purist. You should just have that Miller ratio less than 1. And you're absolutely right. If you have very high gate resistance internal in your device, it's A, not a good design, but B,
absolutely. It's a very, very
exists,
bad.
Alex. Believe me, it exists.
No, but
I'm sure it exists. I'm sure it exists.
It's a really bad design. I
would say come to our website with that.
No, I'm not saying with GaN, but general with other technology.
Absolutely,
you see them. Yeah.
Yeah. But the gate resistance need to be as low as possible within the device for sure. And if you want to slow down or slew rate control, you can do it outside. But internal design gate resistance must be low. Otherwise, your all cells will not be turning on at the same time. And that's a very, very bad thing to do.
But they exist, believe me.
Absolutely. Absolutely. Not necessarily they are the best. Yeah.
No.
Gentlemen, we have the next question coming up. What is currently the maximum practical switching frequency for GaN in low voltage DC-DC applications like 5 volt to POL, taking in account closing loop operations and typical limitations of minimum on and off time of analog IC controllers?
So we do have direct experience with some of that, and it's obviously a very qualified set of answers. The highest frequency that we have on a POL, which is not quite 5 volts, a little higher, like 9.6 volts down to sub 1 volt. The highest frequency we have that's in operation is about 5 megahertz. It's really limited by the inductance at that point. The highest frequency that we have for a hard switching DC to DC converter, however, is 72 megahertz. And that uses a custom digital controller, actually, to achieve 72 megahertz with air core inductors, and is actually quite efficient, 90-something% efficient. There are, I think, Well, I know there is work going on for 100 megahertz plus 5 volt to 0.8 volt POLs, and we're involved in some of that. So 100 megahertz, I think, will be achievable here in the next 2-3 years for a true POL 5 volt down.
Yeah, if I may comment as well, what we see 5 volts and below, we're IC designers, right? So when we see that silicon and GaN, they're pretty much competing there, and silicon is still winning. So especially at these low voltages, we don't see a clear advantage of GaN. So the advantage of GaN starts for us above 10 volt, let's say. So that's one thing. Another thing is this high frequency stuff. Yeah, yes and no, it can be done. So indeed, work 50 megahertz, 100 megahertz, it's being done, has been done in the past as well. I've done some of that as well during my day in my PhD. But the efficiency, is one thing. So I'm not sure if you can really reach those high efficiencies. But
93%, 93%.
Yeah, that's possible, but you have to look at your voltage conversion ratio. If you go from 5 volts to 4.5, that might be possible, but not down to 1. That's one thing. But the other more important thing is the EMI. So at these high frequencies, you basically build an FM radio station, and not many applications may actually like that. So that's something to look into. And if I look at my customers for this point of load converters, then EMI is really a key thing, because you may have many on a system, on a board, and they all are radiating like hell, and that somehow needs to be kept into limits.
Yeah,
so I'd say EMI is definitely an issue. Yeah.
It's not the device; it's actually the system design to start.
Yeah, you can make it as compact as you want, but you'll still end up with an inductor.
Exactly.
If it's an air core inductor, you have a very nice antenna as well. So yeah, this is system level is one thing to consider, which is very important here. Technical achievement is another thing, and we can do many beautiful things in terms of high frequency, but it needs to be workable as well on the system level.
Absolutely.
Thank you, gentlemen. The next question is coming. It's again to all of you. As many of you work also on monolithic integration of GaN ICs, what is the major challenge you see here, and how do you seek to overcome this?
As MinDCet,
what you consider the major improvement allowing monolithic integration in the first place?
Right. As MinDCet, we are doing quite a lot of work on that since many years, but there are other colleagues here that are doing the same thing. I can only speak from our experience, and that is today what we see. The limits to get to higher integration and to higher complexity is the same limit as we have seen in the early 80s, late 70s with CMOS technology. So today we have to base ourselves on RTL logic and RTL techniques, because we have only a low side and we don't have a complementary transistor available. So, and that's really limiting today the circuits that we can build and the power that they consume. So if that's somewhere in the future coming, then there will be a big step forward in monolithic integration with GaN. Not only limited to power, it will then also be able to include analog, digital, and then more system level applications.
Yeah, I mean, I agree with everything that Mike said. I think that it is an evolving technology. I don't think the limitation of RTL technology or RTL circuitry is fundamental. I think that there are opportunities for having complementary devices, but that's a few years off. I think there's another limitation, and that is the stability of the passive components for precision sensing. And in GaN, there's, you've got to worry about things like trapping that is not so prevalent in silicon. And as we harness that more and more, we can get higher precision, certainly resistors and other components, even capacitors have issues potentially. And the other thing is that we don't have a good VREF in GaN. there's not a good minority carrier diode that you can reference. So you've got to play other tricks to get VREF that aren't quite as good yet as they are on silicon.
Yeah, monolithic integration is always challenge in the high power, high voltage applications, and where you'll have to look the pros and cons and where is you draw the line. And for very high power, you probably only would like to integrate the analog part rather than the full digital integration. But obviously it's the system level where you draw the boundary.
If you say high power application, I must confess, in our case, we focus on the switches itself. There is no plan to do further integration.
Yes.
Which this is not the right way for going for high power applications.
Yeah, absolutely. Yeah.
This coming back to the first questions that we already comment, right?
Yeah, and so if I may share screen, this is from the presentation that was just on there, and this is just how we prioritize our integration is to get rid of the parasitic inductances in the system, because those are the things that really limit GaN performance. And so when you integrate it, you get sort of a super advantage from integration. There's no digital logic in here or any of that stuff. So this is just a monolithic power stage, and let's see if I can go backwards here, and it looks a whole lot less complicated. That's the block diagram of that chip, and I think that's a good level of integration. Putting digital controller or even precision analog feedback, I think is sort of a little bit beyond the technology right now.
I agree on that, Alex.
Yeah.
Although I must say, I agree on the integration, of course, and we are also doing this. But the main advantage from my point of view is the fact that you can integrate the drivers and eventually also the level shifters. The fact that you have the less loop inductance on the switching nodes between the two power stage switches, that's also, I very much agree also with that. But the inductance of the ground and the VIN in relation to your bus decoupling capacitor, that is something really up to the system level. So getting rid of those inductances, that is really, I don't see a big advantage of integrating monolithic integration there. So that's really up to the PCB design and the system level design, 3D integration. How well can I fit my decoupling cap as close as possible? That really, so it's, in that sense, it's a multidisciplinary question, right? So it's not, this is a piece of the puzzle that needs to be solved, and that is being solved, like in this nice example. But it's also on system level that you need to attack.
Agreed.
Okay, the last question is coming in. Okay. Is bootstrap technique for gate voltage reliable on hard switching when ringing is present? Could that not cause an overcharging of the bootstrap capacitor and possible damage the GaN device?
Bodo, are you sharing your screen?
Yeah.
I don't think so.
Yeah.
No, we still see the Alex's slide.
Alex, you need to pull your screen back.
Sorry. But
Okay.
Getting too much advertising.
You see how to turn that damn thing off. There we go. Sorry about that.
Enough commercials.
But I can already interpolate on the question.
There we go.
We get it. We get it.
I agree with this question, Bodo. So there is a problem of overcharging when you're doing bootstrapping. And the problem is when for instance, your source inductance on your low side or your ground inductance gets a negative spike during switching, then you'll see, in fact, the bootstrap voltage in addition to this negative spike, and you will overcharge your bootstrap capacitor with a higher voltage than intended. And if you don't do anything about it, you will build up a too high voltage than compared to what you have intended, and eventually you will stress the gates of your GaN device, and you might break it or cause a reliability issue. So we at MinDCet, so there are many ways to deal with this. Of course, you need to minimize inductances. That's of course clear, but that's I think that's opening a door that's already open. But you need to limit that voltage somehow. You can simply burn it off with a Zener diode. That's what many people do, but that's not very elegant and also not very stable over temperature and lifetime. Or you can put floating LDOs in your gate driver. That's something that we did at MinDCet with the MinDCet 901 to make some advertisements, and that's actually working very nice.
Mike, just
a question from my side is this a dedicated problem of gallium nitride, or is it simply a fast switching problem independent from the technology? You can
it's a fast switching problem. Yeah.
So you can have the same when you go for silicon carbide, for example.
Yes.
Yeah. But on that, that's the reason a high threshold cascode is quite forgiving. So whether you have got the 8 volt, 10 volt, 12 volt, 14 volt momentarily, which is a 20 volt gate rating, does help. So this is that's why the in the E-mode design it's quite challenging, but on the cascode design, the bootstrap is quite forgiving, and you can work.
It's not challenging. It's not really challenging. I mean, we integrate a over voltage lockout in all of our monolithic power stages, and all the gate drivers that are made for GaN today have a high side over voltage protection, whether it be from TI or UPI or analog. They all have over voltage protection. It's a real issue, but I think that it is solved pretty simply today.
Yeah, but if you only have the over voltage protection, you will simply switch off your system. So that might not be the way to go. So you need to attack the problem from the base.
It has to be intelligently done for sure. But it is integrated today in all our devices and in all the gate drivers that we use with our devices.
Alex, I think probably the two perspective here. One is your low voltage devices versus our very high voltage. There is, I think, that's where probably sometimes our answers are mostly complementary rather than
conflicting.
Against conflicting, exactly. Yeah. So
no, I think you're right, Dilder, and I apologize for that. But my perspective is in lower voltages.
Yes. I think that needs to be clear to the audience as well. Thanks.
Yeah.
Gentlemen, my backstage tells me that we have efficiently utilized our time slot, and I will thank you all for making the Wide Bandgap event to a success. And I wish you a nice, peaceful Christmas time and a good start for the new year, especially a peaceful one. Thank you very much, gentlemen, and see you soon at one of the real events. And I'm working to get a real event next year instead of a digital.